Okay, so this week we're gonna continue talking about some points of modular inverse. So last week we ended up in somewhere around here, which is that. Okay, so I recap a bit. So for modular arithmetics, we do this because we don't have infinite amount of memory, and so we use an alternative, which is modular arithmetic in our sense. And modular arithmetic is good because it respects addition, multiplication, negation, identity, and multiplicative identity. So many things are good. And then the question that we were asking was that, can we do division modulo? And the answer is yes, but depends. Okay, the answer is depends. So the inverse by definition here is that we have A multiplied by B is congruent to 1 more n. So you can write B as the A inverse or 1/A. And note that this 1/A is different from the regular rational number. It is just a symbol. So then we also prove that a modulo of the inverse of A modulo M exists if and only if yeah, actually we only proved the if statement. So basically if the GCD between A and M is 1, then by Bezout's lemma, there exists an x and y such that ax plus my is equals to 1. So this x is exactly our A inverse. So our A inverse will be x from what we have found from Bezout's lemma. So yeah, but the x can be found using extended Euclidean algorithm, which we talked about last week. So yeah, so for this week, first let's look at the converse of this statement. Here we are basically saying that if GCD of A and M is equals to 1, then the inverse of A modulo M exists. But the converse is also true, as in if the GCD of A and M is not equals to 1, means that there is some common factors between A and M, then the inverse of A modulo M does not exist. So basically, these two together forms kind of a thing that if we know that AX is congruent to 1 modulo M, then we must have that GCD of A and M is equals to 1. Yeah, so that is basically what this is saying. So let's look at the proof of this converse statement. Suppose that GCD of A and M is not equals to 1. So this means that the GCD is some G that is greater than 1. But now let's suppose by contradiction, so this is for the sake of contradiction, that an inverse exists. We want to prove that this is impossible. So we want to show that x cannot exist. But we suppose that x exists now. So if x exists, right, then we can expand the modular equation to get ax plus km is equals to 1. And then because g is a factor of A and g is also a factor of M, we can factor out g and rewrite it in terms of g multiplied by A divide g times x plus M divide g times k is equals to 1. So because so note that these two are integers, and this whole thing is also an integer. Okay, so now we have this equation, and this basically already gives us a contradiction. Why? Because this part is an integer. However, the multiplies of two integer with one of the factor g is greater than 1 can never be equals to 1. So because, like for example, if g is 2, then for what k that you multiply, this can never be equals to 1. So that's the reason. Therefore, x does not exist because g can never be 1. So because this equation can never be true. Therefore, we prove the statement that if the GCD of A and M is not equals to 1, then the inverse of A modulo M does not exist. Okay, is this okay? Okay, great. So now we move on to the next part, which is basically just some example on actually finding a inverse. So let's say suppose we want to find inverse of 3 modulo 5. How do we do it? So we can perform extended Euclidean algorithm on 3 and 5. Then we have that 3 multiplied by 2 plus 5 multiplied by -1. So this is 6 and this is 5 and -5. So this is equals to 1. Which is why the inverse of 3, the x here is 2. So so 3 inverse is equals to 2, not 5. Okay, so the next example. Now if we want to find inverse of 4 modulo 15, we can do the same thing again. So perform extended Euclidean algorithm, then we get this, and then 4 multiplied by 4, this is 16. 16 is congruent to 1 modulo 15. So 4 inverse is congruent to 4 mod 15. Okay, so now let's look at another example. So in this case, we have 4. We want to find the inverse of 4 modulo 14. But if we perform the extended Euclidean algorithm, we see that the GCD of 4 and 14 is equals to 2. So this is not equals to 1. So just now we proved that if it's not equals to 1, then the modulo inverse does not exist. So the answer of this is does not exist. Okay. And then a brief remark here. So in general, we would want to modulo a prime number p because all the integers in the range from 1 to p minus 1 will have an inverse modulo p. This is because prime by definition is just so because all this number inside this range, we have that this will not divide p. So this will create a good situation which addition, negative multiplication, and division are all well behaved, even with finite memory. So a good example for this is like, for example, you can modulo 5, and then you can check that all the elements other than 0 has an inverse modulo 5. Okay, so this will build out this will build out why are we using 2 primes when you are dealing with RSA afterwards. Okay, so far any questions? Oh, good. Okay. Okay, great. Yeah. So now let's look at modulo equation. Because we have we already established this situation which that addition, negative multiplication, and division are very well behaved in modulo p. So we can now and try to solve some equations modulo of prime number. Yeah. So let's look at this. Actually, this 15 here is not a prime number, but it doesn't matter. It's basically the same thing. How do we solve the equation 5x plus 5 is equals to x mod 15? You use the usual way. Then so you move this towards this, and then you minus x on both sides. Then you move 5 on the other side, which will give you 4x is congruent to minus 5. So minus 5 is basically 10 because you can do minus 5 plus 15. So this is 10. And then you multiply 4 inverse on both sides. Then you get, or you can think of it like this is just like pulling 4 to the other side. Then 4 inverse modulo 15 is 4 because we have proof. I think we have shown here. 4 inverse modulo 15 is 4. So this one is 4. So, and then you multiply this together, you get 40. 40 you modulo 15, which is equals to 10. So yeah, so x is equals to 10 modulo 15. You can check by plugging in the numbers. So you put like 5 multiplied by 10 plus 5 is equals to 10. No, we check whether this is equals to 10 modulo 5. So this this will be equal to 55. 55 is got 30, 45, right? So you can minus with 45, so which is equals to 10. This is just 15 multiplied by 3. So indeed, this is correct. Okay, but now let's look at another example, which is slightly tricky. So like for example, okay, so we have 5x plus 5 is congruent to x modulo 16. Then again, we move x to the other side, then we get 4x is congruent to minus 5 modulo 16. Then 4x is congruent to 11 modulo 16. So now, so now the issue here is that you see 4 and 16, the GCD of 4 and 16 is equals to 4. So this part here cause that so basically we basically 4 inverse does not exist, which is what we proved just now. Because the GCD of 4 and 16 is not equal to 1. So for here, right, we can see that 4 and 15, the GCD is equal to 1, so we can find an inverse. But in this case, 4 and 16 is not, the GCD is not equal to 1, so the 4 inverse does not exist. Then actually, so how do we proceed in this case? We can't really like pull it to the other side already. And in fact, you can try to expand out what happens when this situation happens. So we look at this example. Okay, wait. It's this. Okay, never mind. Okay. Let me see the chat. 15 from, yeah. So because negative value, you can always just add back. Modulo, when we talk about modulo, we usually will write it in like the smallest positive integer. So negative integer, you just add back the remainder. No, not the remainder, the quotient, which is you can just add 15 here in the case. Okay, so yeah, suppose we just look at this situation. We don't care about the 11 here first. So we just look at 4x modulo 16. So for 4x, right, if the GCD of 4 and 16 is not equal to 1, then you realize that no matter what x you put, right, the result will always have a factor of 4 inside. So what I'm saying is basically that no matter what x I put, let's say I put like 3, this will become 4 times 3 modulo 16. And then 4 times 3 will still be divisible by 4. So so basically, no matter what things that you put, 4x will always have a factor of GCD between 4 and 16. So maybe it will be much clearer if we look at this example. So we want to find x such that 5x plus 4 is equals to x modulo 16, and then we do the same thing. We pull this x to the other side, and then we get that 4x is equals to minus 4 modulo 16, and then 4x is equals to 12 modulo 16. So in this case, we kind of okay, we know that 3 is the answer here, right? Because if we plug in 3, then this will becomes 4 times 3, which is basically 12. So that's our answer. And then but then we cannot pull this to the other side because 4 and 16, the GCD is not equals to 1. So this gives us a little bit of issue because sometimes the solution exists or the solution could not exist in the case of 4x is equals to 11. So this case, there are no solution for this. But then for here, we know that the solution is 3. So how can we check whether a solution exists or not, or even if it exists, how can we systematically find out the solution? So that's the question that we want to work on. So suppose in that scenario, which we mentioned just now, we have that GCD of A and M is equal to G, and this is larger than 1. And we also have that GCD of A and M divides B. So now we can expand out the modulo equation. So after expanding out, we get AX is plus KM is equals to B. And then because all sides, this thing has a factor of GCD of A and M. This thing also has a factor of GCD of A and M. This thing also has a factor of GCD of A and M. So I can just pull out the G on both sides, and all these three remains as integer. So if all these three remains an integer, then I can remove the G, which gives us a new equation, which is A divided by G times X plus M divided by G times K is equals to B divided by G. So we can then convert this back to modulo by just doing modulo. So we write modulo M divided by G, and this term will disappear. Then we get that A divided by G multiplied by X is equals to B divided by G. And this are both integers. So in this equation, so after we divide by G, right, the nice property about this is that this and this will now be co-prime. The GCD will become 1, because by definition of GCD, we just divide the greatest common divisor. So there are no divisors. If they are still left with some divisors, then the divisor that we divide on is not the greatest anymore. So by just doing so, we make sure that this term and this term has a GCD 1. And now the inverse exists, and then we can use extended Euclidean algorithm to solve the equation. So more explicitly, let's look back at the example of how do we do this. We have that 4x is equals to 12 modulo 16. Then we divide this by the so the GCD and 4 and 16 is 4. So we divide this with 4. We divide the term with 4, and then we divide the modulo with 4. Then in the end, we'll get that x is congruent to 3 modulo 4. So that is our final solution. And you can check. So 4 times 3 is equals to 12. And then 4 times 3 plus 4, this is equals to, this is 7. So 7 times 4 is 28. So 28 modulo 16 will be 12. Yeah. So we basically, so in the case that the term here and the term here has common factor, and then you cannot just find the inverse, you can just divide by the greatest common divisor and then get a new equation here, and then you solve from there, which is very convenient. And what happens if we cannot divide? If we cannot divide, then the solution doesn't exist. Like for example, the situation which this 4x is congruent to 11 mod 16. So 11 cannot divide by 4. After you divide, then this is not an integer anymore. So in this case, the solution doesn't exist. So yeah. Okay. Any questions? Okay. Right. Everything okay? Okay. Great. So yeah, and I leave this as an exercise on how to find x. Which we have that 3x plus 4 is equals to x plus 2 modulo 12. So the thing is basically the same. You move this over, you move this over, then you get that 2x is congruent to minus 2 modulo 16, and then you just work out the rest yourself. I think I put it. I will put it in the exercise afterwards also. Okay, yeah. So now let's look at some very interesting application for modulo arithmetics or Like why is this modulo interesting? Not in terms of like I say not in terms of like computational problem. It's just on like mathematically why is it interesting. So suppose you want to check this number whether it's divisible by 3 or not. I'm not sure if you have learned this before in school, but basically what happens is that you can just add each of the term together. So if you add like 4 plus 3 plus 6 plus so on until 2, and then you see whether this is divisible by 3. So if this is divisible by 3, then we know that this is divisible by 3. But why is this even the case at the first place? So now we are trying to we will try to prove this statement. So usually we write numbers in base 10. We can rewrite number in base 10. Oh, sorry. Yeah. So we can rewrite number in base 10 as something like that. So like 2 is basically 2 multiplied by 10 to the power of 0. And then this one should be, okay, I think there's a mistake here. Wait, 4, 3, 6. Yeah, okay, I copied additional. Yeah, and all this should be 8. This should be 8, and this should be 7. Okay, just rewrite this quickly. Yeah. So you see, 2 is basically 2 multiplied by 10 to the power of 0, which is 1. And then 8 is basically 8 multiplied by 10 to the power of 1. 3 is 10 to the power of 2, and so on. But then we know that 10 modulo 3 is equals to 1. So this basically means that I can convert everything into 1. I can simplify the equation. I convert everything into 1. And then 1 is just all the, so basically you just add all the terms together, right? So, okay, after you completed this, this will become 36. You can repeat this procedure again, and then this become 3 times 10 plus 6. So you add 3 and 6 together, then you get 9, and then you get 0. Right. So, very common trick that you might have used it before in secondary school when you want to check divisibility. And this is why it is true. So, not just 3, this is also possible with 9. Again, I have the same mistake here, but I just don't care about it anymore. This should be cancelled off, and then all this should be turned into 1 less power. But 10 modulo 9 is equals to 1 modulo 9. It's equals to 1. So it's basically the same thing. So you just add everything together, and then you can just repeat the process and then get that. Check whether it is divisible by 9. So another classic example is 11. When we modulo 11, we know that 10 modulo 11 is equals to -1 modulo 11. And -1, so you can rewrite it in terms of like just I also add an additional term here. Yeah, but basically you can rewrite it as 2 multiplied by -1 to the power of 0, and then yeah, just repeat everything. So what happens is that, oh, I think I just messed up the whole things, but yeah, I just messed up everything here. So okay, so this should be add, this should be minus, this should be add, this should be minus, this should be add, this should be minus, this should be add. Yeah. So basically you just add alternative terms and then minus the alternative terms. So yeah, this is so wrong. Okay, so I'm so sorry about that. But I'll just rewrite this. So if I want to check whether this is divisible by 11, then I write it in terms of like, so I can do like 2 minus 8 plus 3 minus 2 plus 1 minus 6 minus 7 plus 6. So and then I check whether this is divisible by 11. Yeah, so you can work out the things yourself, but I believe this answer is wrong. Okay, so this should be wrong. Okay, so yeah, just a very fun technique on modulo arithmetics. Any questions? Yeah, number theory is very fun, right? Sometimes it can be more interesting than yeah. And you can also check it like, let's say if you represent things in other bases. Like for example, if you represent things in like base 5, then if you want to check whether it can divide 4, then you can just modulo 4, you just add all the terms together. Okay, so yeah, now we move on to the next thing, which is called Chinese remainder theorem. Okay, the main reason that we want to talk about Chinese remainder theorem is we are interested into solving this kind of equation. So we want to find x such that just now we were looking at only a single modulo equation, but now what if we have two modulo equations? We have two constraints in some sense. So if we have two constraints, of course, okay, so how do we do it? One way is that we can brute force, and if we brute force, then we can check that 13 is the solution, because 13 modulo 3 is equals to 1, and then 13 modulo 5 is equals to 3. So x can be 13. So if we put x as 13, then it is one of the possible solutions. And you can also check that 28 is also one of the solutions. So Chinese remainder theorem basically tells us a way to solve this kind of questions. Okay, to write it down more formally, let P and Q be two numbers that are co-prime. So I didn't write down the definition of co-prime directly, but basically, if I say two number is co-prime, it basically it means that the GCD is equals to 1. There are no common factors between them. It means that they are co-prime. So if two numbers are co-prime, then we can find a unique x modulo PQ such that the system of equation holds. So this is just saying that we can find. So I haven't shown you how to find. So the theorem says that we can find. And it can also be easily extended to have more equations, and each of the individual Pi and Pj is co-prime. So how can you view this? Because like you can just do it one by one. So we can do like these two together first, and then you combine this and do with the next one, and then it's just iteratively combine. But because it is pairwise co-prime, so you can just easily add more equations and it will hold. So the reason why this theorem is called Chinese remainder theorem is because it is first known to be written down as a statement by Sun Tzu, and this is Sun Tzu Suan Jing in one of his book. And basically, I think the history is like the army is like they are trying to hide the number of like people in the army, like with this kind of modular equation and some sort like that. So if you are interested in the history, you can again go look it up. But it is only formally write it down in like by Euler, I believe, Euler, in the like 70s or 60s. No, yeah, okay, I forgot the years, but yeah. Okay, so now how do we find such an x? How do we know whether an x exists? Okay, so the intuition of the construction is like that. First, we try to prove the existence of this, right? We try to construct a number x such that this whole. So we let x n, a big N, to be the multiples of all the p's, all the modulo. So this will be P1 multiply P2 multiply P3 and so on until Pn. Then we construct x by writing K1 multiplied by n divides by P1. So n divides by P1 here means P2 multiplied by P3 multiplies everything until Pn. And then n divides P2, this will equals to P1 multiplies P3 multiplies P4 and so on until Pn. Basically, you just take out one of the terms from each of them. So here you take out P1, here you take out P2, and here you take out Pn. So the interesting thing about this is that let's just ignore the k first. So k is just an arbitrary coefficient that we put it down. So notice that when we modulo P1, all the other terms will become 0. The reason being that we just take out one of the terms from each of the coefficients. So like this one, I take out P2, so it has a factor of P1 inside. So it has a factor of P1 here, and then here also has a factor of P1. And all the terms except for the first term will always have the factor of P1 inside. And you can so if I construct it like that, right, then what happens is that when I modulo P1, all this becomes 0, and then I'm only left with the first term. So now that I'm left with the first term, I have some freedom that I can I have some freedom to manipulate the values, right? So how do we manipulate it? So we multiply by a k1, k1 in this sense, and we want to make sure what? We want to make sure that x modulo P1 is equals to A1. So we solve the equation for K1 such that K1 multiplies by N divides by P1 is equals to A1. So here Ki is explicitly constructed such that this multiplied by this will becomes Ai modulo Pi. And just now I already showed that we can solve so this is known, right? This is known. This is also known. And then this Ki is our unknown factor. And then this thing also invertible in Pi because of the co-prime statement that we said just now. So NPi inverse exists. So Ki is basically equals to the inverse of N divided by Pi multiplied by Ai. Okay, so we just repeat this, right? And then for each of the Ki, we just set it like that. Then because a solution exists because of GCD of this, and this is 1. Therefore, X is the system, a solution to the system of equation here. So by explicitly constructing it like that, we make it that this thing will hold. And you can think about it, right? This is kind of like arbitrary. Like you can, like, why would you like try and do something like that? And then it's basically like a trick in some sense. So you want to make every terms independent from each other. And by doing so that you can, by making the independent thing, then you can have the freedom to change to whatever you want. So this is only proving existence. But Chinese remainder theorem says something stronger. It says that this X, the answer that we find is unique. Basically, it means that we don't have, if we construct it that way, this is the answer that we get is the unique answer. Like we won't get any other answers than this. So now we want to prove the uniqueness of Chinese remainder theorem. Before that, I just want to make sure that everyone is good with the construction. Okay. Okay, great. Yeah. So the uniqueness is proved like that. Suppose we have two variables, two values, x and y. What that satisfy the system of linear equation. So now I'm trying. So the usual trick to prove uniqueness is that we have two solutions, x and y. Then we want to prove that x. We have many steps. Then in the end, we want to prove that x is equal to y. So that is usually how uniqueness is proved in many theorems. So suppose we have these two that satisfy the linear equation. By definition, we know that it should satisfy this whole part. So this whole part should be satisfied. So we can write it like that. Basically says that x, this part is independent. You can think of like this is by the definition of y is the solution, and then this and this is a definition is by definition of x is a solution. So you can just equals everything together. So then next, we only look at this part. If we look at that part, we can move x to the y to the other side. Then we get that x minus y is congruent to 0 for all the P1 to Pn. So this basically says that x minus y is a multiple of n, because recall that n is just P1 multiply everything to Pn. So this is just multiple of n. So if x minus y is multiple of n, it means that x minus y is congruent to 0 mod n, which means that x is congruent to y mod n. So x is unique. So we basically, in the end, we prove that x is equals to y. But it's in terms of like modulo n. So it's unique up to modulo n. Okay, so that is the proof for uniqueness. And also the proof for Chinese remainder theorem. So in general, right, we might not be able to get like co-prime modulus pi, pj, like this might not always be the case. Like for example, we could, like we want to solve equation, and equation could be very arbitrary, and this might not be the case. But we can always solve for this modulo equation as long as this equation holds, then we can find a solution. And the solution is guaranteed to exist if all the modulus are pairwise co-prime. Yeah, because this is always invertible in a pairwise co-prime scenario. Okay, so that's Chinese remainder theorem. I will show some example afterwards. But any questions on the proof? Okay. Then okay, so now I'll move on to the example. Yeah, so this is just practically like try and work out the x. Suppose that x is congruent to 1 modulo 3 and x is congruent to 3 modulo 5. We let n to be 3 times 5. 3 times 5 is equals to 15. And then remember how we did it just now? We just divide the n with the first term, which is 3. You divide the n with the second term, which is 5. This will become 5, and this will become 3. And then we want to find K1 and K2. So what is K1 and K2? K1 is we want to solve this equation so that this and this is the same. So K1 multiplies 5, we want this to be equals to 1 mod 3. And then K2 multiply 3, we want this to be 3 mod 5. And here you can just solve this individually, just look at each of this individually. K1 is equals to 2 because 2 multiplied by 5 is equals to 6, and 6 is 1. Wait. Yeah. Sorry, this is 10. Yeah, 10 is 1 modulo 3. So plug back the values in. This is 10, this is 3, so the answer is 13. Which aligns with what we say just now, because we say that the answer is 13 and the answer is 28. And exactly that is what we have. 13 mod 15. 38 modulo 15 is also 13. So another example, we want to find x such that this thing holds, which is mod 2, mod 3, and mod 5, and then this is 1, 2, 3. We divide by 2, we divide by 3, we divide by 4, 5. And then, yeah. And then you just do the same thing. Okay, so this is this should be 1, and this should be 2, and this should be 3. So you just solve for K1, K2, and K3, and then you get that the answer is okay. So 15 modulo 2, this is 1. So K1 multiplies by 1 is equals to 1. So this K1 is equals to 1. 10 modulo 3, this is also equals to 1. So this is K2, just 2. This is also equals to 1. So this is just 3. And then we just multiply everything together. We add them out together. This is equals to 53. 53 modulo 30 is 23. So 30 is this big N. And you can check 33 modulo 2 is equals to 1. 23 modulo 3 is equals to 21, 2. So this is 7 times 3, right? 7 times 3 is equals to 21. So you just minus that. And then 23 modulo 5 is equals to 3. So this is our right answer. Okay, and then final example, which is that suppose we have two primes, right? We want to find the x such that x is congruent to 1 modulo p, x is congruent to 1 modulo q. So it could be very complicated, right? So we might not know. We might not know P and Q. So in the case of RSA, right? So sometimes we don't know P and Q. But here we know that the answer is 1. Because because you can just eyeball, right? So if you put 1 inside, then 1 is congruent to 1 modulo P and 1 is congruent to 1 modulo Q. And by uniqueness of CRT, 1 is the exact answer of this 1 is the exact answer of this modulo n. Yeah, so that will be yeah, so the answer for x will be 1. Okay, so any questions on examples? Practice makes perfect. Yeah. Okay. Then so Chinese remainder theorem is okay. So now we move on to the next big theorem, which is called Fermat's-Little theorem. Okay. So just now we were wondering on what happens when we have multiple equations, right? Multiple like multiple modulus. So what happens when but that doesn't say anything about like power operations. So to be more exact, we want to look at what happens when we do something like x to the power of p modulo p. So when we when we do like power operations in modular arithmetics, what will we get? That's the question that we want to ask. So we just look at a very simple example first. We consider sending x to x squared modulo of prime p. Okay, so notice that x squared is equals to minus x squared because minus x multiplies by minus x is equals to minus 1 square multiplies by x square. So this is equals to x square. Okay, this seems very trivial, but it actually says kind of important things. So after applying the square operation to each of the element modulo p, that will give us at most this number of distinct element left. So so let's just look at an example. Suppose we start with 0, 1, 2, and 3, and 4. Then we just square all the elements, right? We square this and we square this, we square this, we square this, we square this. So 1 square is equals to negative 1 square. But remember that negative 1, when we do modulo, is equals to the last element minus 1. So like the modulus minus 1. So this will just be equals to 4 square, which is equals to 1. And then the same thing, 2 square is equals to negative 2 square. Negative 2 is equals to 3 square. So 2 square is equals to 3 square. So this is 4. So after applying the square operation on the set, we are left with only 3 elements. 0 always stays the same. That's for sure. But then the other 1, 2, 3, and 4, we're only left with 1 and 4. Reason being that in modular operations, right? X and minus x, different elements. These are different elements. Usually are different elements. Unless that unless you have the situation and x is equals to minus x. But this is usually a different element. So if it's different element, then after you performing square, you have two elements that will map to the same item. So like here, in this case, you have 1 and 4 will become the same. And then 2 and 3 square will become the same. So this is why we will have that p minus 1 divides by 2. Because p minus 1 is just 1, 2, 3, 4. All the numbers exclude 0. Then this number will divide by 2. And then I plus 1, which is contributed by 0. So the number of elements left will just be this much. Okay, so yeah. After we apply this operation, we kind of like shrinking the set size. But now let's look at what we've applied. What if we apply the cube operation? So we look back at the same example, 0, 1, 2, 3, 4, modulo 5, and then now we apply the cube. 1 cube is equals to 1, 2 cube is equals to 8, modulo 5 is 3, 3 cube is equals to 27, 27 modulo 5 is 2, 4 cube is equals to 64, 64 modulo 5 is 4. So you realize that after we apply the cube operation, we get back the original set. In some sense, it's like a bijection. Like after you map it, you get back the original thing. You wouldn't crash. But when we are doing square, we will always have crash because the negative value and the positive value will always map back to the same thing. But then when you apply cube, it will never crash. Actually, it kind of depends on what modulus that you put. But from what we see here is that it never crashes. So now this raises an interesting question. What power will give us back the original set? And then can we just determine the size of the final set by just looking at the powers that we are working on? So that is the interesting question that we think about. So to actually determine the size of the final set, that involves a little bit of group theory, but I will not talk about that because if I talk about that, then there will be another 3 sessions that I need to cover. So we just look at one simple example or one simple consequence, which is the Fermat's-Little theorem. So the Fermat's-Little theorem says that suppose we are doing modulo p and we are raising to power of p minus 1, everything will crash into 1. So it basically says that after applies the p minus 1 power modulo operation to the set from 1 to p minus 1, we only left with 1. So everything will crash together and becomes 1. Okay? So why is this the case? The proof is here, but I will just skip it first. We look at some examples. Suppose we have 1, 2, 3, 4 and modulo 5. And then p minus 1 is 4 because the prime is 4. 1 to the power of 4 is equals to 1. 2 to the power of 4 is equals to 16. 16 modulo 5 is 1. 3 to the power of 4 is 81. 81 modulo 5 is 1. 4 to the power of 4 is 256. 256 modulo 5 is 1. So we see that this is true. Okay. But how do we prove this? Okay, we try to use non-group theory method to prove this theorem. So first, we multiply both sides with x first. So we multiply both sides with x. We multiply x here and x here. So and then we try to prove that x to the power of p is congruent to x modulo p. So now to prove this statement without using group theory, we need to use mathematical induction. Okay, not sure if you all have learned that before, but yeah, so we have to prove base case and then the inductive case, and then we basically say that this is true for everything. So suppose that, okay, it's clear that the statement is true when x is equal to 1, right? Because 1 multiplied by whatever powers will always be equal to 1. So 1 to the power of p is equal to 1. So now we suppose the statement is true when x is equal to k. We attempt to prove that the statement is also true if x is equal to k plus 1. So okay, if this is true, right? Because just want to talk about the intuition of like mathematical induction. So we don't look at how the proof works out first. But if x is k is equals to true, if this is true, then if I can use this statement to prove that this is true, because we proved that x equals 1 is true already, then this can imply that x equals to 2 is true, and it can imply that x equals to 3 is true, and so on, until however large number that you want. So that's how mathematical induction works, which is that you assume that the previous case is k is true, and then you try to prove that k plus 1 is true. Okay, yeah. So how do we prove this? Okay, we just take x plus 1 and then we raise to a power of p, and then we see what happens. Okay, so x plus 1 raised to a power of p, then you use binomial expansion, which is that which you get that this is basically p choose 1, pc1, pc2 until pcn. Oh, this should be pcn. Yeah, pcn. No, pcp is 1. Yeah, okay, this is correct. So we just expand out the binomial equation. So yeah, so this will be PC1, and then this will be PC2. Just in case you all don't know, like we have that, like for example, this is x squared plus 2x plus 1, and this is 2 choose 1. So then we also have like x, suppose it's this one, then it's like x cubed plus 3x squared plus 3x plus 1. This is 3 choose 1. This is 3 choose 2. Yeah, binomial expansion. Okay. So one thing, the nice thing about binomial expansion is that PC1 until PC n minus 1, you always have a factor of p inside. So when I do modulo p, this thing will become 0, 0, 0 all the way. Everything here will become 0. And I only left with x to the power of p plus 1 modulo p. And then because we suppose that the statement is true when x is equal to k, so x to the power of p, this is the previous case. Okay, actually this should be k plus 1. Sorry, I think I messed up here. Yeah, sorry, this should be k plus 1. Everything here should be k. And this should be k. Okay, yeah, k. So k to the power of p by inductive hypothesis, this will be equal to k. So this will be equal to so k plus 1 to the power of p will be equal to k plus 1. Therefore, the statement is true when x is equal to k plus 1, and by induction hypothesis, Fermat's-Little theorem is true. So we have that this is always true. Okay, any questions? Okay, good. Right now, the last part of today's sharing, which is the application of Fermat's-Little theorem. So okay, just now we said, okay, so remember this. So this Fermat's-Little theorem is very important in number theory. X to the power of p minus 1 is equals to 1 modulo p. If you don't want to, if you think the proof was too difficult to understand, it's fine. You just remember this. This is enough. So now with this itself, we can prove this statement. We take any prime p and then a power d. This will always hold. This says that x to the power of d is congruent to x to the power of d modulo p minus 1. So basically, it says that we can reduce the operation on like the power. So we don't have to like compute so large. We can just like do the modulo operation on the power and reduce the size. So why is this true? So for Fermat's-Little theorem, we have this case, right? And then x to the d, we can rewrite it in terms of like that. So this is basically just saying that x d minus kp minus 1 and plus kp minus 1. I just add and subtract the same thing, okay? And then I pulled out the positive part out. So x to the power of kp minus 1, I can rewrite it in terms of like x to the power of p minus 1 and then raised to the power of k. X to the power of p minus 1 by Fermat's little theorem is 1. So this is k. And then 1 to the power of k is 1. So this is 1. So it says that I can deduct my d with however many times of p minus 1, and the modular equation will hold. So x to the d mod p minus 1 is equal to x to the power of d modulo p. Okay, so an example on how this works out is like, let's look at this huge thing. We have a very huge power, but from this lemma right here, because we are doing modulo 5 and 5 is a prime number, then we can just push the modulo up to the so we can just modulo p minus 1 in the power, in the power. And then if you can just calculate this very easily. This is just I just use a Python program to calculate this. This is basically just 2. So if this is 2, then the answer is this. So the answer. So you don't really need to. Okay, so let's say if I give such a large number, you can't really compute it out, right? But the Fermat's little theorem is good is because that it says that you don't really need to compute it out. Like you can reduce your problem. You just in the end you just need to calculate 3 to the power of 2, which is 9, and then 9 modulo 5 is equals to 4. So this is nice because we sort of like reduce our computation by a lot. So another example is that we have 3 to the power of 6 to the power of 1000. So 6 to the power of 1000 is an imaginary, it's a very, very large number, and we can't even like imagine it. But then modulo 7, because we do modulo 7, we can do minus 1 on top of the power. So 6 to the power of 1000 modulo 6. This is just 0, right? Because 6 times 6 times 6 for 1000 times modulo 6 is just 0. So 3 to the power of 0 is 1. So we have that. 3 to the power of 6 to the power of 1000 modulo 7 is 1. Okay. So you might see, okay, so this kind of fractions is like if you go for like mathematics competition in high school, in middle school, sometimes they will ask this kind of question, and you just use all this formula. It seems very hard, but it really isn't. It's just applying the formulas, applying the theorems. Right. Okay. Yeah. So that is the end of today's sharing. That's all the contents that I have. So next week I will talk about Euler's theorem, and then finally we can talk about RSA. Okay, and any questions? This won't work when E is equals to 2, 5. Depends on your size of the. So okay, in RSA, right, we have P is like a very, very large number. And then when E is just 2, 5, 5, 3, 7, you can't really do any reduction because this is already like smallest. So yeah, why you can do all this interesting thing is because the modulus here is small, and then you can like just yeah. But if this is a very large number, you can't do anything as well. Like let's say if you do like 3 to the power of 10, you modulo like 100, you can't really like do any reduction. Not 100. Maybe let me choose a better prime number like 97. Like you can't really do any reduction because 10 modulo 96 is just equals to 10. And then you know that 3 to the power of 10 is certainly much larger than 97. Okay. The exercise. Yeah, right. Maybe I should share about the exercise. So okay. Let me share my screen. Okay, so I think I haven't released it, but wait okay, let me release it now. So I have like 8 questions prepared for this just regard to the content that we teach this week. And then so you can try and do it. And I think we are giving out some merch for the first few to finish the top few to finish all the exercises, including the previous one. Yeah, but please try and just do it and not like immediately Google for answers, because I think it's more interesting if you can like learn something out of it, like rather than just like go for the prize. The prize is just an incentive for you to finish it, but don't like just rush the questions because you want to win the prize. I think that is not that good. Okay, yeah. So all the challenges are here. From modulo 2 to modulo 4. And it's basically the same thing, the same few things. If you have if you encounter like any questions, like you feel that your answer is correct, but the flag is like not the system is not accepting your answer, then you can like just let me know. Maybe I made a mistake.
Okay. Thank you.
Yeah.
So
that's all.
let me close the recording and stop.